So as you see here, we have a grid, and for the sake of time, I'm not going to draw it, fill it in completely with the rows and columns. But we have a 9 by 9 grid, and I want you to imagine that right now, or draw that right now. And further, we have the numbers 1 through 81 on this grid. Well, she's trying to calculate the product in each row and column, and she's trying to find the least number of rows and columns that would have a product divisible by 3. So how many numbers are multiples of 3 from 1 through 81? Well, we can see that 3 is 1, 6 is 1, and all the way up to 81. And 3 is 1 times 3, and 81, the last multiple, is 27 times 3. So as you see, there's 27 multiples of 3. How will this help us? Well, we're trying to find the product in each row and if it's divisible by 3. So if a number or one of these multiples of 3 are, first, let's just imagine that it's right here. This entire row, and this entire column, this entire row will be divisible by 3. So we're just gonna have to. So how do we minimize this? How do we minimize the number of rows and columns that have a product of 3? Well, one way of not doing it and actually maximizing the number of rows and columns is forming a diagonal. As you think about it, if we have a diagonal across and we have all these 9 boxes filled with the numbers, the multiples of 3, then each row and each column will be divisible by 3, which will maximize what we're trying to minimize. So I'm going to draw it again. And the best way in this case of minimizing it is creating a box or a rectangle. And you'll see why this works later, but we can't create a box because 27 is a perfect cube, not a perfect square, but we can create a rectangle. And how will creating a rectangle help us? So if we have a rectangle right here, only these rows and columns will be for a better word contaminated. So these multiples of 3, if we just imagine, they're contaminating these rows and columns, and if we group them all together, they'll contaminate less rows and columns. So, and obviously, the longer we can try multiple different rectangles and see which ones work. But let's just say 3 times 9. 3 times 9, obviously, it's still a rectangle, so it's minimizing it. But we're contaminating 9, let's just say, rows and 3 columns. So if we drew this out, let's just say this is 3, this is 9. We're contaminating 9 rows up. No, 9 columns up and 3 columns to the side. Okay, so that would equal 3 plus 9 is equal to 12. But there's a better, more efficient, even smaller, even minimizing the number of rows and columns that would be contaminated by multiples of 3. And that would be 4 times 7, which is 28. So we have enough boxes to contain these multiples of 3. And 4 plus 7, 11 rows and columns contaminated. So that is the smallest amount that we can have. Even let's just say 5 times 6, that's also 11, and that's 30. And we can obviously test, but that 11 is the smallest the least number of rows and columns that would have a product divisible by 3. So the answer is D. And now we're going to move on to problem 17. The solution. So as you see here, we have another grid problem, which I don't know why they put next to each other. with the other grid problem. But anyways, we have a 3x3 grid, a smaller grid this time, which is good. And we're dealing with two kings. And instead of calling it the white king and the black king, we're just going to call it the first king and the second king to make it simpler. Okay, so we have the first king and the second king, and we're trying to place these kings so they don't attack each other. Obviously, we can eliminate one of the cases right here, and that's the first king going into the middle square or the center square. That's because it attacks all the other squares next to it and all the squares remaining. So the second king can't even get placed down. So that's obviously eliminated. But now we can go to we can start with two cases. So the first case is corners. And what I mean by that is the first king getting placed in the corners. So there are 4 corners right here. And the first king can get placed in any of these 4 corners. So let's just say the first king gets placed in this bottom left corner. Well, we can see what the options for the second king. So the second king can no longer go here, the center square, go in the center square. I don't know why my pen is right here. The center square, and then the square above it, and the square right next to it, to the right. So the second king can only go in these 5 squares right here. Because again, the first king attacks these squares. Okay, so there are 5 options. So the first king has 4 corners to choose from, and the second king has 5 options when the first king picks a corner. And all the corners have the same scenario for the second king, so we are keeping that in mind. So that's 20 ways. There's 20 ways for the first case, and now we're going to go on to the second case. The second case is what we're going to call edges. And what do I mean by edges? So the first king can get placed when we're not considering the corners and get placed in the edges. On the edges. Right here. So again, similar to the first case, there's 4 edges. Oh, I don't know what happened here. What? Okay, anyways, that was a weird glitch. Okay, there's 4 edges that the first king get placed in, and once a king gets placed in on an edge, let's just say right here, the second king can only go in these go in 3 squares because the king attacks all these 5 squares bordering it. So after a king gets placed on an edge, the first king gets placed on an edge. The second king only has 3 places where it could get placed. So we add up all the ways, and using these cases, we make sure that we don't overcount, and we also don't miss any ways. So there are 20 plus 12, 32 ways of ways that this can be done. So the answer choice is E. We can start with the smallest circle. The smallest circle has a radius of 1. The second smallest circle has a radius of 2. So this is 1 and 1. This length is just 1 and 1. So this is the largest circle. This is the medium circle, and the first one is the smallest circle. So, and then it says the region between the 2 smallest circles is shaded. We obviously know that, as in is the portion of the region between the 2 larger circles bounded by central angles BOC. So it's asking the shaded and unshaded it's telling us that the shaded and unshaded regions are equal. So we're gonna use S for shaded and unshaded as US. They're equal. So their areas will be equal at the end. Okay. What is the measure of angle BOC? So we're not going to start with the measure of the angle first. We're going to first start with the areas of the circles. And let's start with the smallest circle. So the smallest circle is obviously unshaded and has an area of pi. And that's the first thing. And oh wait, shoot, I put in the wrong category. Unshaded. So the unshaded category has pi, or the small circle, in it. And then now we're gonna continue with the shaded region. So the shaded region, let's just look at the medium circle and anything within it. The medium circle has a area of 4 pi, radius of 2, and it's in order to find the shaded region of this circle, we have to subtract the inner circle because it is unshaded. Now, inner circle has a area of pi, so 4 pi minus pi is 3 pi. So the shaded category has 3 pi and pi right now in the unshaded category. Okay, so and we also know that the large circle, or uh, the unshaded and shaded regions, will have a total combined area of 9 pi, because the largest circle contains both the unshaded and shaded parts. And it's saying right here that they're equal. So if we divide 9 pi by 2, we know that the shaded region will have 4.5 pi, and the unshaded region will also have 4.5 pi. So now we're just looking at, since we already incorporated everything, middle circle down, or middle circle, the inner part of the middle circle, we're just looking at the outer ring. And the outer ring kind of looks like this. Kind of looks like a donut right now. And it has a shaded part and an unshaded part. And that will help us determine the angle measure. So the unshaded part obviously needs 3.5 pi more. So the unshaded part of this donut, let's just shade this in real quick. The unshaded part of the donut will have an area of 3.5 pi, and the shaded part will have an area of 1.5 pi. 1.5 pi because it needs to get to 4.5 pi. Okay, so, and now we can just find the angle measure, because if we see, we have a center right here, and this is our angle measure right here. We're just measuring, measuring the shaded part over the entire part. Because if you think about it, the angle measure is including the shaded part, and the entire part is just including the shaded and unshaded part. So the shaded part has an area of 1.5 pi, and the total area of the donut is 5 pi. So we have 1.5 pi over 5 pi, and that's just, let's just see, 3 pi, 3 over 10, I believe. Actually, yeah, 3 over 10. And obviously, 360 is the total angle measure of a circle, and we get 36 times 3, or 108, as the angle measure of the shaded part. So the answer is A. So 15 sneakers, or 15 pairs of sneakers, and 3/5 of the pairs are red. So 3/5 of 15, that means there are 9 pairs of sneakers that are red. And the rest are white. So we can easily find out that there are 6 white pairs of sneakers. This is 15 minus 9, it's just 6. Okay. And then now separately, there are two-thirds of the pairs are high top. So there are 10 pairs that are high top. And then the rest are obviously low top. So there's 5 low top pairs. And it's asking the red high top sneakers make up a fraction of the collection, and it's looking for the least possible value of this fraction. So the red, there's nine red pairs of sneakers, and let's just cross. And in order to have the least red high top sneakers, we have to pair these low top sneakers with these reds. Okay, so we're gonna have 5 red low top. Low top sneakers, or 5 red low top pairs of sneakers, and now we're down to 4 red pairs of sneakers, and there's no more low top. So obviously the 10 high top pairs has to be 6 white and 4 red. So there has to be 4 red high top sneakers left or remaining. And that's our obviously already the minimum number there could be, because obviously there's all the low tops are now red. Okay, so there's 4 and there's 15 pairs in the entire collection, so that's 4/15 as your answer, C. So as you see here, P has to be the vertex of the equilateral triangle, and in order to form an equilateral triangle, the 2 other vertices have to be an even number of edges away. So as you see, V, let's see, V, I believe, and R. Shoot, I don't know why my pen isn't working. Yeah, my R and T are the only vertices that can be part of the triangle. And obviously you can test this by forming equilateral triangles and seeing which triangles are actually equilateral or not. And as you see here, we have to choose 2 of 3 vertices, because we already have P as the vertex, or one of the vertices. And 3 choose 2 is just 3. Answer is D. Obviously, a probably simpler way would be just seeing which equilateral triangles exist and could actually exist. Like if you see right here, 1 unit wouldn't work because obviously that isn't equilateral, but 2 edges away would work because they're all 2 edges away. So yeah, 3 triangles can be formed, and now we're going to move on to problem 21. So we're going to start right here. A frog turns green when in the shade, and then it turns yellow in the sun. And the initial ratio, so the starting ratio from green to yellow frogs, was 3-1. So we can write, use G as the number of green frogs. Actually, no, we can use G as a portion of the green frogs. So there's 3 portions in this ratio. So there's 3 green frogs to 1 1G, or the amount of yellow frogs in that ratio. So then the 3 green frogs move to the sunny side. So if 3 green frogs move to the sunny side, they become I believe, yellow frogs. So we subtract 3 from the green side, or the number of green frogs currently, and we continue on. So 5 yellow frogs move to the shady side. So 5 yellow frogs are now green, so we add 5 again to the green side, and we get 3G minus plus 2. And originally there were G yellow frogs, and now they gained 3 and lost 5, so now they're down 2, so subtract 2. And now the ratio is 4-1. So we can write 4/1, or the number of green frogs now over the number of yellow frogs now, or what we have right here, the same ratio, and it's 3g plus 2 over g minus 2. And then we can solve this ratio. So obviously the ratio is the same. This is the number of green frogs. This is the number of green frogs, or the number of portions of green frogs. And then we have g minus 2 and 1, which represents the number of yellow frogs compared to the green frogs. Okay, so we can cross multiply. Obviously, there's different ways of solving it from here on out, but we will get the same answer, and that's g is equal to 10, and I believe y. And we're looking for the difference between the number of green frogs and the number of yellow frogs now. So all we have to do is plug it in right here, and we find out that there's 32 green frogs now, and there's 8 yellow frogs. So we find that the difference is 24. So as you see, we don't have to have two separate variables, green G and yellow for green frogs. We just have to have green frogs to make it one variable green frogs, or G, to make it much simpler to solve. And yeah, that's how you solve problem 21 solution. So as you see here, the entire roll of tape is 4 inches in diameter, or 2 inches inches of radius, and 2 inches for its radius. And as you see right here, it's wrapped around a ring, so that ring is not made of actual tape. So we have to consider that. And then it says the cross section of the tape is shown. The tape is 0.015 inches thick. So if the tape is completely unrolled, approximately how long would it be? So we have to find that we can find the area of the rolled tape. And doing this, obviously, we can just use the radiuses and the areas of the circles. So the larger circle is 4 pi, because it has a radius of 2. And the inner circle, it has a radius of 1, so the area is pi. So that means 3 pi is the area of the roll tape. And if the tape is 0.015 inches thick, well, we'll have to put inches right here, thick, then how long would it be? So all we have to do is just divide, because we want to see how long it actually is. Because this is the area of the rolled tape, and if we unroll it with this being the length, the width of it, then we'll find the length. And obviously having a calculator would be best, but you don't really need a calculator, because you can pi is around 3.14, and that's around like 9.42, and then divided by 15 over, let's just say, I think 100, I believe. Yeah, 100. Actually, no, that's 15 divided by 1,000. And then we can just calculate that, and we see that's around 600-ish. It says round your answer to the nearest 100 inches, and it's around 600-ish. So the answer choice is B. Now we're going to move on to problem 23. Solution. So he first starts with these points, 0, 4, 2, 0, pretty basic, pretty small. And then he increases the size by a lot. But we don't have to worry about the increase of size. We just have to think about it in a smaller way. So I'm going to draw a graph similar to this. And so obviously we can draw a figure similarly to this, what a diagram that they have provided us, but we could also use a grid system because a grid would be much better. So if we have a grid system right here, we can have equal cells, somewhat equal cells, and we can see how many cells are actually passed or colored. And obviously when we use these coordinates, we have to keep in mind that we can divide them by 1,000. So it's much smaller. So this is 2, 3. And if we move over 1, so this would be 3, 4, 5. And we go up 4, 5, 6, 7, and 8. We get 5, 8. Obviously, we divided by 1,000 as well. And all we have to do, oh shoot, I'll just write it 2 at this side. So this is 5, 8. This is 2, 3. And all we have to remember is multiply by 1,000 the number of cells colored. That will help us. Okay, so as you see here, we can just draw a line, and you'll have a ruler on the test, so that might be beneficial to when solving this problem. We'll see how many cells are colored. So there's 1, 2, 3, 4, 5, 6, 7. There's 7 cells colored, and you can obviously use the slope or any other details that will help you guarantee the number of cells colored. But in this case, we just used a line and we drew it, and we found out that there's 7 cells colored. And we have to multiply by 1,000 because in the larger scale, there's going to be 1,000 more cells that are colored. There's just a smaller representation that we shrunk down. From the larger representation. So now we get 7 times 1,000, 7,000. The answer is C. Now, so as you see here, I already see something in the figure. Again, there's 45-degree angle right here. There's a 90-degree angle right here. We have to have another 45-degree angle. And how do we do that? Well, we extend. And we make a 45-degree triangle. And this will help us in the future. And we could do that to the larger triangle, or a larger triangle that's going to be formed. So we have 90 degrees, 45 degrees, and now we have another 45 degrees. And as you see, we formed a small triangle as well in this process. So again, this will help us later. The artwork has an area of 183 feet. This will help us later. But anyways, we can find the areas of these 2 larger triangles. And this might help us find the area of the smaller triangle later, which will help us find the value of h. So we're first going to start on the left. We're first going to start with this triangle. So it has a height of 8, and using that 45 degrees right here, we know that half of the base is 8, and a leg is 8 square root 2, 8 root 2. The other leg is also 8 root 2. And the height of this, and then obviously using to find the area, all we have to do is multiply 8 root 2 by 8 root 2 to get 128 divided by 2, 64. So the area of this triangle is 64. And the area of this triangle, this large triangle, we can do the same. 12, 12, and 12 root 2, and then 12 root 2 on the other side. Or even we can just use the base and multiply by the height. There's different ways. But we get 12 root 2 multiplied by 12 root 2, 288 divided by 2, 144. So now we found the area of both these triangles. And if we see, we found the area of this triangle, we found the area of this triangle. What are we overlapping twice? What area are we overlapping twice? Right here. So if we subtract the area of this triangle, which we can find as well, let me erase all this. So if we find the area of this triangle, which is just, let's see, h squared root 2, h squared root 2 on this side, we get h squared as the area of this triangle. We subtract it, and we get the area of the total shaded region, 183 square feet. And whoa, everything seems to fit. Now we can find the value of h squared, and we can find the value of h as well. So we subtract 183, we get 25, and then we get that is equal to h squared, and then h is equal to -5 or 5. -5 obviously doesn't work for obvious reasons. It can't be negative. And we get h is equal to 5. So we have 4 rows right here with 3 seats in each, just to visualize more clearly. And I hate the wording of this problem. This problem can be turned into a much simpler problem. So we have 4 rows with 3 seats, so that means we have 12 total rows, 12 total seats. And the problem gives us there's passengers, 8 passengers. So obviously for the purpose of this problem, we're gonna make sure that we're gonna suppose the passengers are indistinguishable. And we're going to switch this question up. So what it's really asking is, if 4 empty seats are placed, what is the probability that there are 2 adjacent seats open? That's basically what it's asking. There are 4 empty seats that are placed. Obviously, look, there's 12 total seats, 8 passengers. If there are 4 empty seats placed, what is the probability that there are 2 adjacent seats open? And we're going to start with casework. So, case 1. There is exactly 1 pair of open seats, and there's going to be 2 other seats that are not in the same row, and they're not going to be adjacent to each other. Not going to be in the same row as the pair of open seats, and they're not going to be adjacent to each other as well. So we're going to first start. There's going to be 1 pair of open seats, and if there's 1 pair of open seats, there's 8 ways to choose them. As you see, there's 2 pairs per row, so that means there's 8 total ways to choose them. Now we're going to move on, and we're going to have 2 empty seats. So there's going to be 2 empty seats, and they're going to be distributed throughout these 3 rows. Other rows, because empty there's already 1 pair of open seats in this row, and obviously if the empty seat is right here, there's gonna be 3 in that row, which is a no. So there's gonna be 2 empty seats non-adjacent. I'll just say that are not adjacent. Okay, so how do we count this? Well, there are 9 seats to choose from. It cannot be in the row with the pair, and 9 choose 2 is 9 choose 2 minus 6. And what is this minus 6? Well, there are 6, we're overcounting, and there's 6 ways where the 2 empty seats are adjacent. So we have to subtract those, and we get 30 cases. So there are 30 cases per pair of open seats, and for a total of 240. So 30 times 8, we get 240 cases. And this is only the first case. Now we're going to move on to case 2. Case 2, and there is one row of open seats. So there's one row of open seats. We're going to select one row for these open seats to be. And again, the couple can be in any of these seats, any of these pair of seats. Again, and then there's going to be one empty seat. Well, the one empty seat is easy because all we have to do is choose one of the 9 open, and for the row, there's 4 choices. So there's 4 times 9, 36 cases for the second case. And now we're going to move on to case 3, the final case. And in this case, there's going to be 2 independent pairs of open seats. And what do I mean by this? What do I mean by 2 independent pairs of open seats? Well, hold on, let me erase this real quick. Well, what I mean is that there's going to be 2 pairs, but each pair is not going to be in the same row. So basically, what we're choosing is the possibility of these pairs to be where the couple sits. And that means there are 4 choose 2 options for where these or 4 choose 2 ways for cases where these 2 rows are chosen of the 4 rows total. And there are 4 ways to arrange these pairs within its row for a total of 24 cases. We add up all the cases, 24 plus 36 plus, I believe, 240, and we get 300. And again, as I said in the beginning, the passengers are indistinguishable, so that means there are 495 or 12 choose 4 or 12 choose 8 ways of placing them at the beginning without the cold couples thing. So there's 12 choose 8, and just basically the 8 people are sitting in 12 seats, which means that if we're trying to figure out the probability, there's 300 total cases where it works. The couple gets their pair of seats, and there's 495 total cases. We can simplify that as well, and we get 20 over 33. So the final answer for this problem is C. If there's any problems or concepts you want to go over, please leave them in the comments down below.